Welcome to Session 5 on Signal Grounding Concepts and Examples. A brief review of the two reasons for grounding. We discussed in Session 4 that there's safety grounding, which may require multiple connections or may involve multiple connections. And then there's signal voltage referencing. Again, I want to stress that returning currents back to their source, very important, very essential to reducing noise, but completely unrelated to grounding. The second reason for grounding, other than safety, is providing signals with a proper reference. That's not the same thing as returning signals back to their sources. You would hope that in your designs it would be easy for you to identify which are the grounding conductors and which are the signal return conductors. Now, I know this is kind of a trivial example here, but maybe this is a good place to start. If we can get it right in the simple cases, maybe then we can extrapolate this to the more complicated situations. In this situation here, I would say the return conductor is this conductor here. And I would say the grounding conductor is this conductor here. This is a non-current carrying grounding conductor, and this is a current carrying return conductor. Now you could rightfully ask, how do I know this is the return conductor and not the other conductor? Since this is likely going to be an AC source, first current's going in this direction, and then a half cycle later, the current is reversed. Well, maybe it doesn't matter that much, but usually if one of the two conductors is grounded, that is considered the return conductor. Now notice, we're talking here about discussing a ground-dead conductor where the ending is ED versus a grounding conductor where the ending is ING. To many electronics people, grounded conductor, grounding conductor, return, common, neutral, heck, it's all the same. You know, why get excited about the differences in these words, right? It's just a question of semantics. It doesn't really mean anything, does it? Well, no, I think it means a lot. My way of saying this, if we use the incorrect word, then we've got the wrong idea in our mind, and we're going to try to build the wrong thing. If we're saying it's a grounding conductor when it's really the return conductor, it's just not going to come out right. It's not going to work properly. We're going to have noise problems as a result of that, and probably some safety problems also. So the words are critical. The words represent ideas, our concepts, our strategies that we're trying to implement. If we've got the wrong word, we've got the wrong idea in our mind. So it's not just semantics. It's a lot more basic than that. And safety people, they know the difference between a grounded neutral as opposed to the safety grounding conductor. Make a big difference between those two. So this conductor, this is a grounded conductor, but it's not the safety grounding conductor, which is this one over here. Anyway, the main distinction between whether it's a signal conductor or a grounding conductor is, does it carry a significant amount of current on purpose? If it's supposed to carry current, it can't be part of the grounding system. It has to be part of the intended signal path. So that's the easy way to tell the difference. Do we intend for the conductor to carry current or not? Now, another critical question is, how many times should a signal be grounded? A lot of times people will say, well, probably only ground the system once. But now notice, I switched words on you there. First I said, how many times should a given signal be grounded? And then I said something about how many times the system would be grounded. A system might be grounded multiple times, consisting of many, many currents. The real basic question, though, is how many times should any given current be allowed to be grounded? Let's try to figure that out using this example. Here I show a simple system consisting of two currents, and here's a ground structure. Now this ground structure can be whatever you want it to be. It can be building steel, it can be the frame of a satellite, the metal frame of a ship, or the frame of a car, or whatever is a reasonable ground structure for you. Let's assume that we're going to make a direct conductive connection to ground. Maybe I should switch over to a black pen because now we're going to be talking about non-current carrying. we make a conductive connection to ground from current loop I1. Now the reason for the question mark there is I want to know why do we think that's a good idea? What's the reason for that grounding connection? Let's assume for the moment that there's a safety mandated requirement. Safety requires that we make this connection. See, my concern is I do not want to allow noise currents in the grounding system to be able to get up onto the signal wiring. And here we have a direct connection. Of course, we have capacitance to ground also, don't we? At multiple places, kind of a distributed capacitance. So we do have more than one tie to ground. One is metallic, others are capacitive. So there is going to be a slight amount of current from the grounding system circulating up onto the signal path. But again, assuming that the ground noise voltages are at low frequency, and assuming these capacitors are not that large, maybe the amount of circulating ground current is allowable. We'll assume that it is in this case. So I think we could get away with this. But supposing current I2 has a similar need. This goes into a grounded circuit in a metal box, and maybe this metal box requires safety ground. So again, there's another connection over here. Again, I want to know why, but I'm saying that maybe in some sense, unfortunately, from a signal point of view, unfortunately, there is a safety requirement that's likely going to give us a little bit of difficulty here. Well, these two metallic ties to ground don't necessarily need to lead to a serious problem. If the signal isolating device, the transformer, if it's doing its job, we may still be okay. In fact, we may now see why there's a need for this device. The isolating transformer breaks up what could otherwise have been a very low impedance, that is, high current carrying ground loop. If the capacitance from the primary side to the secondary side, if that capacitance is small enough for the frequencies involved here, this could be an acceptable situation. So I would say so far, if we've designed it for this configuration, we could be okay. That is, if we've designed to have adequate isolation between the two sides of that transformer, that we could tolerate more than one grounding connection on the system. The system has two ties to ground, but each current only has one conductive tie to ground. Now supposing we try a little further here. Let's say we add another grounding connection on current 1 over here, a direct tie to ground, not capacitive. Well, then we're out of luck, I believe. Now the low frequency ground loop currents are going to be able to circulate into circuit 1 area without much limit. Ground noise currents have access to the low frequency, low level signal path, and unfortunately our low frequency signal has access to the grounding path. Now we've gone too far. This is not allowable, at least not normally. So here's the general rule that I think we can come up with. Normally, a given current might tolerate one conductive tie to ground, but we don't want to have multiple conductive ties to ground. One may be tolerated, but not more than one. Now, see what I'm saying? I'm not saying that every current should have a conductive tie to ground. I'm saying that that is probably the most we can allow, is one direct metallic connection to ground for any given current within a system. More than that, in most instances, is going to be a problem. Now, do you think there are any exceptions to this rule here? Well, this is like all the rules we're going to give out and talk about. They all have exceptions, and that's where the trouble comes in, is knowing when to apply the rule and when not to use it and so on. Let me mention a couple of exceptions to this rule right here. Supposing we have what I'll call RF currents. And let's say what I mean by that is the bandwidth of the current, let's say it goes from 1 to 100 megahertz. Note that the key thing is no frequencies below 1 megahertz. Well, we already said most of the ground loop noise is in the kilohertz range. Sometimes it's a few tens of kilohertz, but mostly low kilohertz. So in this situation, if this particular current is multiply tied to ground, then what's going to happen? Those low frequency ground currents are going to get onto the signal wiring. And those low frequency ground currents are going to cause low frequency noise voltages to exist within this RF circuit. But not a problem. we just filter it out. Everything below 1 megahertz we don't care about. So we can put a little series capacitor in our signal line, block out all that 60 hertz and 540 hertz and 180 hertz and 2 kilohertz frequencies and not have a problem. We're not interested in what's going on at low frequency as far as our signal is concerned. So because of the low frequency end is not that low, we're in good shape. RF currents, like they're typically run on multiply grounded coaxial cables, that's not a problem. But supposing we have a video signal. Let's say the bandwidth goes from DC to, well, the classical video used to be like 6 megahertz, but now we got all this high-speed graphic stuff. It maybe goes up to 100 megahertz in some cases. But the problem really is not the upper end. Most of the noise trouble in a video signal like this is going to occur from DC up to maybe 1 kilohertz. That's where all the noise trouble is going to be. So this is a type of signal which we do want to be careful about. If we multiply ground, conductively tie to ground more than once this kind of signal, we're going to have low frequency, usually power line harmonic noise bothering that particular signal. So that kind of signal, I think, would have to follow our rule. The rule which says normally we only want one, no more than one, conductive tie to ground. Another example of a signal that might be grounded more than once would be a signal operating in a very well balanced circuit. Now we have a later session where we're going to explain in some detail what is balance and what is the advantages of it and so forth. But a well balanced circuit, if grounding does not destroy the balance, then we can use the balance as a protective measure to guard against trouble that would normally come about because of multiple tie to ground. So if the circuit remains balanced when it is multiply grounded, that may allow us to still combat the problem. Now here's kind of a difficult question. And we're going to take several minutes exploring this to try to find out how to answer this question, what to do. Should an internal signal reference, that is the reference for a circuit which is in a metal box, should that internal signal reference be in any way connected to the surrounding external metal chassis? Now, of course, the answer, as you might expect, is yeah, sometimes you want them connected and sometimes you don't want them connected. And what we've got to figure out is what are the situations that govern when we make the connection between the signal reference and the metal enclosure, and when do we not make the connection. Also, we need to figure out at what frequency do we make the connection. Do we make it at all frequencies, or do we only make it at high frequency and not at low frequency? Those will be the issues we have to concern ourselves with. Here's a situation that involves a safety concern. We have a metal chassis which is properly safety grounded. Now this would be the primary safety ground, the one that parallels the phase conductor, the one that provides the fault current. This grounding connection here is not the most important safety ground. This is the one. But anyway, we have inside of here AC powered circuits, transformer coupled. Let's assume that the dashed connection is not present initially. So we have our electrical circuits floating. But we do have a wire coming from the circuit to the outside world. What's the voltage on that wire relative to ground, to earth, building steel, or whatever we consider ground to be in this area? Well, if this circuit is isolated from the metal housing, this common mode voltage, as we're going to call it, we don't know what it is. In fact, it could easily be 40 or 50 volts AC because of the capacitance across the transformer windings, between the transformer windings. So this could present a bit of a safety concern. If we take one side of our circuit, and usually we take the negative side of the power supply, but it could just as well, I guess, be the positive side. But if we took one side of the power supply, directly bonded that to the metal housing, then the voltage between at least the negative wire and the housing would be approximately 0 volts. So, this is the reason why a lot of people will tie an internal signal reference, the negative side of a power supply, say, to the external metal housing. It's to guarantee that when wires come out of that housing, there might be 5 volts DC or 12 volts DC on some of those wires, but there's not going to be 40 or 50 or 60 volts AC on those wires. The common mode AC voltage will have been shorted out by the connection from the power supply to the metal housing. So for added safety, we will often tie the internal signal reference to the external metal housing. Now in this situation, it's not critical where we put that connection. We could put it here, or we could have put it internally anywhere. As far as safety is concerned, the precise location of that connection is not too important to us. Here's another situation. Let's say we have a sensitive printed circuit board inside a metal enclosure, and we've got a multi-conductor cable coming into this enclosure to connect to the circuit board. I'm just showing one wire in this cable for now, but one wire is all it takes to be a problem here. Let's assume that electrostatic discharge could occur to this wire. Now you usually can't discharge to an insulator. You have to discharge to a metal, some conducting material. So maybe we're talking about the metal pin of the connector exposed, or maybe the end of the wire is somehow exposed. With the insulation around the wire, if it's adequately thick, we'll not be able to discharge through the insulation to the wire. But somehow the wire is exposed, and the electrostatic discharge can get access to the conducting surface. Let's think of the discharge as coming from a capacitor that is charged relative to a ground structure, several thousand volts. Let's say that this metal housing is well connected to ground for safety reasons, if for no other reason. Now let's try to identify the path of this electrostatic discharge current. Let's assume that the dashed connection that I show here is not present. This is not present for the moment. But let's assume that unfortunately this dashed connection is put in place. Well, you can see what's going to happen. We're going to encourage the high-frequency ESD currents, at least in part, to come across the surface of the printed circuit board over to the connection to the chassis. Then the currents are going to return on the interior wall of the chassis. Then they're going to come back out the area of the connector to the outside wall, and then they're going to flow back to the source. And unfortunately, this connection at an interior location allows for these high-frequency currents to at least partially come inside the box and flow across the circuit board. When they do, they're likely going to disrupt the operation of some of that circuitry. So I think it's pretty obvious that for improved immunity, that is, reduced susceptibility to incoming high-frequency noise, that we do in fact want to make the connection from the circuit board to the metal housing right in the area of the connector. We do want to connect to chassis right at the connector, and the connector location is critical. Some arbitrary internal location is not going to be very good for us. So for high-frequency susceptibility, to keep high frequencies out of the metal enclosure, yet wires still coming into the metal enclosure, we want a connection between those wires and the enclosure, but we want it right at the point of entry, right at the connector. Of course, we can't bond all wires directly to the box, but some wires may be directly bonded. Other wires will probably capacitively connect to the enclosure. But the key point is, for high-frequency susceptibility, to reduce that problem, we do want the signal referenced to the chassis, but right at the connector area, not at some internal location. What about high-frequency emissions? You might expect, rightfully so, that what's good for emissions is probably good for susceptibility and vice versa. So we know what works for susceptibility. We might expect it to work here. Imagine we have some high-speed digital circuits on a printed circuit board in a metal enclosure. Now I show say it's a clock line. I show this clock trace quite some distance up above the plane of the board. That's just to make it easy for you to see. This is not quite drawn to scale. In fact, the lateral dimensions here would be much larger probably than shown. The vertical dimension much smaller. What I want you to be able to see is this. Supposing we have a connection again between the back edge of the board and the box, the point where I say no, we probably shouldn't have. So say we have the connection there. On the other side, we don't have the dash connection yet. Imagine high-speed digital currents circulating in this clock loop here. You can kind of identify that loop. In fact, if we're doing a good job laying out this board, we want to know exactly where that loop is located. But there's one loop. Look between the printed circuit board and the metal housing. That's a second loop. If a tiny amount of magnetic flux passes from one loop into the other loop, that's going to induce a voltage in the second loop. And the voltage on the second loop will be between the circuit board and the metal box. And that voltage will drive the external cable like a monopole antenna. And we'll have common mode current coming out on this antenna. What's supposed to be a non-radiating cable, but actually turns out to be a radiating cable, and we'll get electromagnetic emission coming off of that wiring. So we talked before about how sometimes we have high-speed digital circuits unintentionally coupled to an antenna. In this case, the unintentional coupling is due to a mutual inductance that occurs internally within this box. If instead of this style of grounding scheme, if the connection over here had been left out, but the circuit board return plane, if that return plane had been well bonded to the box at high frequency, and of course that's the trick, getting this connection to be effective at high frequency. If there's a very good connection here, then we're basically shorting the signal wire to the box. We're not able to maintain a voltage difference there. We're not able to drive the dipole antenna. The fact that we have a connection internally, that might, if we had a connection internally, that might be allowable as well. But the preferred approach would be to have a very good low impedance, high frequency connection between the circuit board and the box, again, at the connector area, but not at a point internally. Now let me discuss a little bit more about how this magnetic field problem occurs, because this ties in with our first session where we were talking a lot about inductance, self and mutual inductance, and stray magnetic fields and so on. Let's say we have a trace above a plane. And this is our high-speed digital trace, and we're looking at it in cross-section. The current flows into and out of the screen. Okay, so we've got current going in and current coming back out in the metal plate. Now we said at high frequency the current concentrates mostly right under the trace. But it does spread a little bit. Now if we were to look at the magnetic flux, and I'll draw this in blue, most of the magnetic flux is going to take the short path. That's the path of least reluctance. 98% of the magnetic flux, just as a rough number, 98% or maybe more will encircle the smaller conductor. But a small fraction of this flux encircles the larger conductor. I'm saying maybe this is 2%. It might even be less than that. This is 98%. It turns out that in many EMI problems, it's not what is 98% of the current doing, or in this case 98% of the flux. It's what is the remaining 2% of the current, or in this case, what is the remaining 2% of the flux? Where is that flux going? If that flux is not under control, and it's not in this case, then we're going to have a problem. Because this flux that wraps around the wide portion of the circuit board, that is exactly the flux that we're talking about in this picture here. That's what's wrapping from one loop into the other loop. We need a way to be able to control that. If we can control that, then we can diminish the coupling between the two circuits, the high-speed digital circuit and the antenna circuit. But of course, if we have the right connection for our circuit board, that can help us control the problem as well. Here's a different situation. Let's say we have low level, say millivolt, low frequency, say kilohertz signals here. Let's say that this signal is electrically bonded directly to the box on this side and capacitively connected by the other lead, and then directly bonded to this other chassis on the other end of the cable. Now we have the ground loop problem we discussed earlier. We have two direct metallic ties to ground. There's going to be a voltage difference between these two ground points, and that voltage difference is going to conductively pass right up onto this signal wire. Or also there could be magnetic noise picked up in this loop. But in this situation, do we want the signal reference in each of the two chassis tied to the metal box? I think the answer here is no. We do not want these multiple connections to the box, because then we get into a conductive ground loop problem. So to avoid the low frequency ground loop problem, we're going to need to remove one of these two connections. I show the one again on the receiver end, this one being removed, because usually that's the easier one to remove. We take our, what was mistakenly built or designed as a grounded input single-ended receiver, convert this over to a differential input receiver, and then keep this wire isolated from the box except maybe through a capacitor. Capacitively couple both of these leads to the box. That'll help us reduce electrostatic discharge energy from coming in. And if there were some digital circuits over here in some part of this equipment, that would help reduce high-frequency digital circuits signals from being emitted. But we avoid the metallic connection, and that avoids the low-frequency ground loop problem. So the question, should we tie the internal signal to the external metal box? Well, the answer is yes, if you're interested maybe in improving the safety of the situation. The answer is yes, we want to make a connection, but we have to be very careful where. We have to do it at the connector. We want to make the connection between the signal reference and the metal box at the connector to reduce high-frequency emission and to reduce high-frequency susceptibility. But we don't want to make the connection if we're concerned about a low-frequency, low-level ground loop problem. Then we would avoid the connection. At least we would avoid the connection at low frequency. Maybe we don't have to avoid it at high frequency, so we can have our cake and eat it too. We can have the ground loop avoided because we have capacitive tie to ground rather than a conductive tie to ground. Let's talk a little bit again about grounding. This time it seems to be tied in with what we talked about in the previous session on single point grounding versus the ground grid approach. And it is related to that. But I want to make sure you understand that a single point connection of grounding conductors, probably that's a good thing. It might be a good thing. It's not always the only way to do it, and it isn't always the best way to do it, but it's a good chance it could be the thing we want to do. But a single point connection of return conductors, 90% of the time, that's a bad thing to do. And it can be a very bad thing to do. It can be a disaster. So you see, we have to be clear now. When we're connecting conductors to a single point, are they non-current carrying grounding conductors, or might they be actually current carrying return wires that we have mislabeled as grounding conductors? Well, you see, that's usually what they are. They really aren't grounding conductors. We think they are. We've used that word. We've called them ground, and they're not. So again, that mislabeling is going to be a disaster for us. It's not just a semantics issue. It's a much more basic issue than that. So let me show you an example. Is this single point grounding? That's the question. Well, this is the way we would say this. We have the sensor ground, the preamplifier ground, and the A to D converter ground. We have all three grounds tied to the same point. That's the way we're going to discuss this. But you see, that's not right. These are not grounding conductors. These are current carrying conductors. Look at how the signal flows. This sensor current comes over to the preamp and then returns by a path like this. 100% of the sensor current is on these two wires that we call ground. Obviously, they're not ground. They're an intimate part of the signal path. Likewise, the amplified signal coming out of here, it returns back like this. So again, this is not a grounding conductor. So you see, this is again a simple example, but it's one that I see, a mistake that I see we make a lot of times. We think we're doing the right thing. We go to a lot of trouble and a lot of effort to get all of these conductors tied to the central point, to the same point, to the single point ground. And yet we're just creating a lot of trouble for ourselves. Of course, you could say, well, what's wrong with this? Why is this a problem? Well, I think we can see. We're increasing the loop area here. We're allowing this signal to pick up all the stray magnetic fields in the area. We don't want that to be happening. And we're also emitting some magnetic fields, causing trouble for other circuits. So this is not a grounding issue here. This is a routing issue. maybe if we take a look, how would I do this? How would I change this? Okay, I would say we've got a sensor, we've got an amplifier, we've got another amplifier, or A to D. Okay, we've got to get the signal out of the sensor into the amplifier, and we've got to get that signal back. I want to get that signal back on a very low inductance path. If it's wiring we're talking about, I'm going to use a twisted pair. That way it's hard to have the two wires 6 inches apart yet twisted together at the same time. So by doing it this way, what I'm doing is I'm concentrating on signal flow. You could say, well, where's the grounding? There is no grounding here. This is just signal flow. Grounding has not come in yet. Then I've got to get this signal over to the other amplifier. How do I get it back? Again, on a low inductance path. If they're traces on a PC board, they've got to be very close together, side by side. If it's wiring, I want to consider a twisted pair. This has nothing to do with grounding. This is all signal routing. Now, after I've got a good wiring arrangement for the signals, then I can come in and ask, where should the circuit be grounded? Should we be grounding the source? Should we be grounding the preamp or grounding the final amplifier, or what? Well, that's now a grounding question, and clearly I don't want to put all three of those in there, but deciding which one of those would be preferable and why, that's the grounding issue. But the grounding issue does not have anything to do with the signal routing. This is a similar example, repeated here again. We've got a little more detail now. We've got a sensor, a low-level sensor in a metal box feeding a preamplifier, a signal conditioner, say, in another metal box, which feeds another amplifier farther down the line. First, you want to make sure that the wiring is such that you have control over the signal path. The way I've done this is a differential receiver. This signal current, this is low frequency. It has no choice but to go over to the differential receiver, go through the differential receiver, and return back on this path. It just doesn't have any other opportunity. Now, this wiring in between, yes, probably it should be a twisted pair, if it's any length at all. But I know where this signal is going to go. It goes on the path I've identified because it doesn't have any other opportunity. What about the low frequency signal coming out of this amplifier? It's only got one path over, and it only has one path back. Now, there are grounding connections shown. There's a grounding connection shown on the input signal here, and there's a grounding connection shown on the amplified signal here. Now, why we chose, say, grounding the signal at this location rather than grounding it, say, on the other end, that's a good question. I'm assuming probably that this was a grounded transducer, that I didn't probably have a choice in this matter of where to put the grounding connection. And again, it's usually easier to have a receiver be isolated from ground. In most instances, that's easier than having the driver isolated from ground. But anyway, first we started talking about signal flow, and I wanted to make sure I knew where the signal was located. Now you see we have capacitors showing between the signal lines and the metal housings in all cases here, where there isn't a direct bond. That's probably for, say, a little bit of ESD protection. And also, if some of these boxes happen to have digital circuits involved that are not shown, that's to help keep the digital frequencies from coupling back out on the low frequency wiring. So this type of connection is for high frequency susceptibility and emissions, improving both of those. Now, how would we do the safety grounding of the three chassis? Well, because signals flow between these chassis and it's low frequency signals, it might help to some extent to have the voltage between the chassis minimized. So rather than just arbitrarily tie the chassis to building steel at multiple different points, I think we'll want to use the single point safety grounding scheme. Each chassis will have a properly sized, properly located grounding conductor, and properly located means it's got to run with the phase conductors. I don't show the power wiring here, but actually the line and neutral power wiring would run right alongside these safety grounding conductors. But by tying all three safety grounding conductors to the same point, we can minimize the voltage difference between the chassis. That minimizes the common node voltage applied to the differential input. And that will help reduce the noise in that circuit. All right, let's take a look now at signal transmission over two different situations. One is relatively short distance, like 20 or 30 feet, to go across the room, say, and another might be signal transmission over several hundred or several thousand feet of distance, or maybe even, worst case, maybe between buildings. How should we handle the signal interface in these two extreme cases? One is a relatively short distance, where the common mode voltage, that is the ground voltage difference, might be only 10 or 15 volts. The other is a much longer distance, where the ground voltage difference might be thousands of volts. There are two different situations. I think there are sort of two standard approaches. If we're running a signal a relatively short distance, I might allow the signal to be grounded at one location, but on the other end, I'm going to isolate that signal from ground. For sure, if this is low frequency, I want to say this is, well, maybe it goes from low frequency to high frequency. If it's got low frequencies, kilohertz frequencies involved, we've got to avoid the ground loop problem. Or another way to say it, if it's got low frequency signals, I've got to get control of the signal current. I've got to force the signal current to stay on only the two conductors that I intend for it to be on. So by isolating the signal receiver from ground, I deny this current the opportunity to flow back through the grounding system. So I would use a differential receiver. Now, we've got to worry about the common mode voltage involved here, the rating of the differential receiver. If it's directly connected, it's probably going to be limited to a common mode rating closely associated with the DC supply voltage that operates the receiver. So if this receiver runs off of plus or minus 12 volts, probably the common mode voltage is going to have to be less than plus or minus 15 volts. Maybe we ought to even say conservatively, let's keep it less than plus or minus 10 volts. So if it's directly connected, then we're going to have to limit the common mode voltage to maybe less than plus or minus 10 volts peak. Well, if we're only running a short distance, probably we can do that by just tying both chassis, again, back to a single point safety ground. That'll mean that the voltage between the two chassis, I would say, in most cases, well, normal operating conditions for sure is going to be less than 10 volts. But you could say, yeah, well, what about when lightning hits the building? Well, if this circuit is near the external wall of a building, we may have a little problem on our hands. We may have a big problem on our hands. But if it's buried down inside of a larger building, even with lightning conditions, running this signal 20 or 30 feet, we might still be all right. Possibly, though, we could put on the input to the differential receiver, we could put some kind of transient protection just in case the voltage briefly exceeds 10 volts. So we've got two situations here. We could have a steady state power line generated voltage, AC voltage of maybe 10 volts, and then sharp spikes. Well, lightning would be maybe a microsecond or so. Electrostatic discharge would be a few nanoseconds or so. But we could have some sharp spikes that could be larger than 10 volts. But we might be intending to attenuate those with some kind of filtering technique. And so we don't expect the differential receiver to see the full brunt of the transient voltage. So maybe with a combination of filtering for some of the high-frequency transients and then single-point grounding to avoid the low-frequency ground voltage difference, with those two combinations, we could make this system here workable. So I think we would isolate the receiver wiring from ground using a differential receiver and then tie both chassis to a single point to help control the common mode ground voltage. What about the other situation where we have signals running a much longer distance? Take the extreme example of between buildings. We're going to have much greater than 100 volts peak. We're going to have kilovolts between these two ground points, maybe every other day or so. We've got a little thunderstorm outside here now, and possibly we've got those kind of voltages existing between our buildings and to some extent within some of the buildings. What do we do here? Here we can't go with a direct conductively coupled path. We're going to have to isolate the signal path. And here I show isolation both on the driver end and the receiver end. The longer the circuit, the more likely we'll need to do both. Isolate both ends. A little shorter run, maybe all we'd have to do is isolate the receiver. Usually the receiver is a little more critical to damage and disruption than the driver because the receiver input tends to be high impedance, where the driver output tends to be lower impedance. But for longer runs, we'd isolate both lines. Now I show transformer isolation, just as something to draw here. If this is a digital signal, we might use optical coupling. If it's analog, we probably would go something more transformer. With analog signals, we need linearity. And transformers are very linear, but they don't pass DC, obviously, so we have to work a way around that somehow. Optical couplers, not so linear, but they're getting better. But with digital signals, linearity is not as important, and we could use possibly that approach. But the key idea is we have to have a metallic break from where the driver is grounded and where the receiver is grounded. We have to have a metallic break, something that's got a high impedance, so that most of this kilovolts will appear across the isolating path, the isolating portion of the path, rather than appearing across the signal return path. Now those are the key concepts we were going to discuss, but let's review a few ideas and take a look at a couple of other ideas also. Does every current need a return path? Well, I would say definitely yes. Every current needs a return path, no question about it. Does every current need to be grounded? No, not all currents need to be grounded. Some do, some don't. When do they need to be grounded? When do they not need to be grounded? We just talked about some of that. Some currents need to be grounded to avoid susceptibility to ESD. Some currents need to be grounded so that the common mode voltage coming out on those wires is less for safety purposes. And then on the other hand, low frequency currents, we don't want to ground them too often because then we'll get into ground loop problems. We want to be careful too to separate the routing of signals from the grounding of signals. I think especially on your schematic diagrams and in the words that you use, be very careful to distinguish between those two ideas. A lot of times I can tell when somebody shows me a schematic, if on that schematic, if the 5 volt digital supply has a digital ground showing next to it, the 12 volt analog supply has an analog ground trace or lead or line showing next to it, all the analog sensor signals have grounds associated with them, well, I know we're in a lot of trouble. We probably need to start over with that idea. If that has actually been built, I think we will have to rebuild it again. But if you see 5 volt digital power and you see 5 volt return, or 12 volt and 12 volt return, pressure signal and pressure signal return, I think maybe now we're on the right track. That's probably a lot better scheme. Now, of course, you can go too far with that. Not every signal needs its own completely separate return, isolated from everything else. Most digital signals can share the same return. Many analog signals, if they're similar frequency, similar amplitude, they can share the same return path. So just like we can completely ignore a return and call it ground, we can also go to the other extreme and think that every signal needs an independent return. That's not true. We need to economize a bit. You can't use that number of wires. You don't have room for all those traces on a circuit board. So we'll have to let those signals which are allowable, have to let them share the same return path. But at least they'll be sharing a return path. It won't be a ground path. We'll know to think of it that way. Let's look at this example. We have a programmable logic controller trying to control a complicated machine that's doing some processing of something. And I'm just showing one sensor signal coming from this machine that we are controlling. Maybe it's a speed sensor, and that signal is being used by the PLC. This is probably a low level, millivolt type, and probably low frequency, probably kilohertz or less, maybe even down to almost DC. So this is exactly the type of signal that's going to be bothered greatly by a ground loop problem. And that's exactly what we have here. The sensor has one side tied to the machine frame. The signal return is tied to the frame of the PLC, the metal box, the metal chassis of the PLC. Now, of course, we probably ought to be asking why those connections. Of course, if this is already built, we don't have a lot of choice in the matter, maybe. So, assuming these connections are in place and they cannot be easily removed or modified, what do we do? Well, actually, I guess what I am going to want to do, I am going to want to change this one. We should have bought a PLC from a different supplier, I think. Why does this thing have a grounded input? Why aren't these inputs differential? If these are all differential inputs, then I don't really care whether the sensor that's feeding me the signal is grounded or not. But if this is a grounded input, single-ended receiver, then I've got to make darn sure that this sensor is not tied to ground. And of course that probably means I can't use the ones we've already got in place. So I would say, yeah, I guess I would want to redesign this or buy it from another manufacturer where I think it was designed correctly. I would want to have these low-level, low-frequency inputs. I'd want them to be differential. Now, you may have a situation where you've got a very large level analog signal, and maybe a single-ended connection would work. But I would probably err on the side of having more differential inputs than I think I'm going to need, than winding up being one short. If one of those low-level signals needs to be connected single-endedly because I don't have enough differential inputs, then we can be pretty sure that's the one that's going to be noisy, and that's going to be continually downgrading the performance of the system. So when low-level, low-frequency signals, when we are not intending to receive them differentially, then I think we should be asking ourselves the question, why? Why not receive them differentially? You say, well, but it's a matter of cost. I understand that, but if we're building 1 million of these, maybe we'll have to look carefully at the cost. I know we will. Every penny is going to count. But supposing we're only building 2 of these systems, and performance of the system is the key thing. So we save a few $1,000s by not buying an additional bank of differential inputs. In the long run, we're going to spend 10 times that amount of money getting the noise out of the system by using the single-ended inputs. So you got 18 channels. You can connect them single-endedly or 9 channels differential. Then I want to see 9 channels differential and just get more receivers if we need to have more inputs. Now there are a few other possibilities. If this is already built and we don't want to replace it all, we could try this. If the noise level is not too bad, we could try reconnecting the safety ground on the PLC such that it ties to the building at the same place where the machine is grounded. So now I'm talking here about using an insulated grounding conductor. Now we've got to be very careful. We don't want to violate any of the National Electrical Code requirements for safety. So I just can't move the ground wire and leave the AC power coming in like it was. I'm going to also have to reroute the entire power distribution system. So we have to keep that in mind. It's not just a matter of moving the grounding conductor. If this metal chassis is only going to have one insulated ground wire, then the AC power line going into that chassis must parallel that insulated ground wire. So we could try to rearrange the AC power. Actually, I think it might be cheaper in the end to just get a differential input. Another possibility, this is not such a good chance maybe, but we could try to short out the voltage difference. You see, the machine is tied to building steel here. Originally, before I modified it, originally the PLC was grounded here. So it was the voltage difference between these 2 ground points, that was our source of noise. If in the area of this equipment, if we're pretty sure that there's a high resistance in, say, the building steel, then we could try maybe to lower that resistance by putting in a ground wire between those 2 ground points and try to short out that voltage. But now keep in mind, we want to be reasonable here. If it looks like the resistance that we're dealing with initially is relatively high, say a few ohms or more, then reducing that down by a factor of 10 is pretty easy. But supposing what we have is basically a steel structure building, and between the 2 pillars in the building we're measuring 100 millivolts at 60 hertz. Are we going to be able to short out that 100 millivolts? I don't think so. I mean, what we're going to do is we're going to probably put a 500 MCM cable. This is a cable with a bundle of copper wires the size of my thumb. We're going to put that 500 MCM cable between these two steel pillars. And we're going to think we're going to short out that voltage, but we're going to be adding a few pounds of copper in parallel with a few tons of steel. And it's not going to make that much difference. We're going to need to lower that resistance by at least a factor of 10 in order to see a big improvement. And it's likely not going to happen. So what I'm saying is, if we can see that in this situation here, between where the machine is grounded and between where the programmable logic controller is grounded, if we see a large amount of steel connected between those 2 points, that is already a low resistance connection. We're not likely going to make it much lower than that. So I don't think we would want to try the technique of shorting out the voltage difference. On the other hand, if the way this was, if the machine we're controlling was in an old building and the PLC is just a few feet away but in a new addition to the old building, and somehow we suspect that the grounding schemes for the new and old buildings are not too well tied together, there might be a bit of high resistance between them, then adding a grounding conductor to straddle that high resistance, to parallel or short out that high resistance, might be a good approach. It's a little bit of common sense. What do we think we're dealing with? Where are we starting? If the resistance is already, 20 milliohms, we're not going to make it any lower. If it's 20 ohms, we got a great chance of lowering that resistance. Let's try another example. This is similar to what we've been doing, but so maybe we would see obviously some of the answers here. We've got a grounded sensor. This sensor is tied to the chassis. We may not like that, but we don't have any control over it, we'll say. We also have a grounding connection on this metal chassis. If there's not AC power coming in here, there might not be a need for this to be a safety ground, but maybe this is a mechanical type connection, just to bolt it somewhere so it doesn't flop around. So in any case, this sensor, this transducer, is directly bonded to the building steel through this array of connectors. We'll take that as a given. Then we're going to run that signal over a few feet of cable, and we're going to try to figure out what kind of cable to use. And it's going to go into a signal conditioner, an amplifier, A to D converter, and then we're going to run it out on a RS-232 serial digital interface line over to a computer where we're storing this information. Let's say the RS-232 line is also a given. I don't like that, but I realize many times we have to start with that. All right. First, I want to take a look at how I'm going to route this low-level signal. I don't want to give this signal access to the ground structure. It has already a direct bond right there, so this amplifier right here, that's got to be differential input. I don't have a choice here. So I've got a differential input, and I'll use a twisted pair. But what this differential input will do is it'll guarantee high impedance isolation of the signal on the receiving end. Now this is kind of a one-line diagram, at least through here. The output of this amplifier may be tied to chassis. But what I don't want is I don't want either one of the inputs tied to chassis. So that's what the differential receiver is going to gain for me. It's going to gain isolation of the inputs from the chassis. So I can be sure that the signal current has to stay on the twisted pair. It's a low-frequency current. If I gave it access to the grounding system, it unfortunately would use the grounding system. Now over here, RS-232. It's a classic, inexpensive signal interface, digital interface. But it's often grounded at both ends. I won't say it's always grounded, but often. And if it's going to be grounded at both ends, then it's going to be susceptible to the ground loop problem, the common mode voltage that exists between the two ground points. If this were a real critical situation, if I were trying to get signals across here where the information was very important to me, and if I only had one or two of these systems, I don't think I'd use RS-232. I would go as the balanced system, RS-485 or RS-422. And again, in a later session, we'll talk about the merits of balanced versus unbalanced a little bit more explicitly. But if this were a very important system and it had to work well under adverse conditions, I don't think I would chance this signal interface that we're looking at here. Because this run over here, this might be a short distance, maybe 5 feet, but this run over here, this could be much longer. This could be 50 feet, could be 100 feet. And so there could be quite a bit more voltage difference between the two chassis. But if it's already built, single-ended, and I'm going to try to patch it up and get it to work a little better, I might try this. I'd look at how the two chassis are grounded that the RS-232 signal runs between. See, I've shown that there's a ground here, a safety ground required, I imagine, but I haven't completed it. I haven't shown exactly where it goes. Well, what I would do is I would use a single point safety grounding scheme. And by using a single point safety ground, I still have a ground loop that is susceptible to magnetic noise, but by contacting the building structure at only one point, I don't pick up nearly so much conducted ground loop noise. Now, you can only use single-point safety grounding when the safety conductors are running relatively short distances, 20, 30 feet maybe. If these chassis were several hundred feet apart, of course, the common mode ground voltage would be a lot worse, and I couldn't fix that by attempting single-point grounding. It just wouldn't be an adequately safe thing to try. In this circuit here, this is really more about routing, but I want to show that, again, we've got to be careful to separate routing from grounding. I want to know, are all of the signal currents under control? The most critical current is probably this one coming from the signal source. That current has a path over and a path back, and no other path. This is low-frequency signal. Remember, if low-frequency signals have more than one path, they're going to use them. Low-frequency currents go everywhere they can possibly go, is basically what happens. And that's a real troubling situation. So the best way to handle low-frequency signals is only give them the one path over and the one path back that you intend for them to use. Don't give them any other opportunity. So we successfully accomplished that with this signal. What about the signal that continues on between the two amplifiers, signal current I2? That current goes over, and then how does it return? Well, unfortunately, part of the current returns there, and part of the current returns on the supply line, the DC supply line to the amplifier. So you see, we might have even used twisted pair wire here. We might have thought we had this loop well under control, but we don't, because part of the current comes here, part of it current comes back through there. And of course, if you check the supply currents, the DC power currents that operate these amplifiers, they're probably two of the most important currents in this entire system. Current I3 goes over to the amplifier, and some of that current returns back here, and some of that current returns back like this. So I think what you're going to see in this example is we have four currents here, at least four that we've identified. I'm sure the system has got more to it than this, but of these four currents, only one is adequately controlled. The other three, we really have almost no control over these currents. So this is a bad situation here. We'd have to rework this somehow to try to get control over these currents. And if you think about it, I think you'll find it's not going to be so easy. Coming up with a scheme, a revised scheme for what I've shown you here that has definite control over all four currents is going to take quite a bit of thinking to figure out a scheme for doing that. Let's take a look at another example. Let's say we have a low-frequency signal which unfortunately is fed over a coaxial cable to a metal chassis, and the coax cable, by virtue of the connectors, is grounded or connected to this chassis and connected to that chassis. And then we have AC power running in with a properly routed and located grounding conductor. Well, because the safety grounding is done adequately, we have an electrically safe situation. But we also obviously have a ground loop here. So it's safe, but it's noisy. That's not too good a result. Let's try to modify this. Well, maybe I'll just show it on this figure here. Supposing I were to disconnect the safety grounds and reroute them over to a central point. Now I would reduce the ground loop noise. I'd bring the noise down, but it would be completely unsafe, because the power wires no longer follow the safety ground. I would have to do both. Again, I'd have to completely reroute the AC power to use a single-point power grounding scheme in order to reduce the ground loop problem and therefore bring down the noise without creating a safety hazard. Actually, what I'd really like to do is get rid of this single-ended receiver, get rid of this coaxial cable, use a twisted pair signal feeding over to a differential receiver, and then we don't have to worry so much about exactly where the chassis are grounded. One last example. Let's say we have a metal enclosure which has RF circuitry inside. We might use the inside wall of this metal box as the high-frequency return path. But very possibly, the outside wall could be tied to building steel and be part of the safety grounding system. The point I'm trying to make here is that sometimes one piece of metal can be both signal return and ground at the same time. That concludes session 5.